Now we're going to try and understand why it is that when you differentiate your unit tangent, it will give you a vector that is always at 90 degrees. The same cannot be said with the tangent. When you differentiate your tangent, it will probably give you something around here. It won't be at 90 degrees. Whereas your unit tangent will always, when you differentiate your unit tangent, it will always be at 90 degrees. So we are going to try and understand why this is the case. So you try and understand why this is the case. It's really the same as you trying to understand this. When a vector is a constant length, then when you take the dot product, it equals 0. Well, if you can understand this, then you can really understand this. So we now need to know the proof for this. Well, the proof is given by this. The proof is given by this. Hang on. So you start here, and the whole proof is this thing here. If you can understand this whole thing here, then skip this video. But now for you to fully understand this, I need to explain the first step, and I need to explain what it means to. Well, I need to also explain the second step. What does it mean to differentiate a dot product? So I need to explain this, and I need to explain this. Why is it that when you take the dot product of a vector of constant length, then you can say it equals to c squared? We need to address this. Okay, so if you understand this proof here, then skip along. But now I need to explain this. I need to explain this first step, and maybe in the next video I will explain the second step. Okay, so the first step here, let's go back. Why is it that when you have a constant vector dotted with a constant vector, it equals some sort of constant square, which is some sort of constant? So we need to address this. Okay, so let's go back to here. So imagine, so going back to our original scenario, we've got a plane flying through space here, and then as it's flying through, this is your tangent vector here. This is your tangent vector. It varies in length. So let's say the plane is here. It may be short. So the vector would be like this, the tangent vector. Let's say over here it's really long. So that's this vector here. Whereas if you look at the tangent vector is always of length 1. So you can imagine this tangent vector to be something like this. It's always, so let's say the plane is here. The tangent vector points in this direction. That's this tangent vector. Let's say the plane is here. It's always of length 1. So that's like this. Let's say the plane is here. This is of length 1. So it's pointing like this. Whereas the tangent, 1 minute is really long. 1 minute is really long. It might not be an ellipse, but let's just imagine it to be an ellipse. So I can explain the concept to you. So let's say the plane is here. The tangent would be quite short, let's say around here. So here the tangent always varies in length, whereas the unit tangent is always of length. It is always of constant length, So why is it that when something is of constant length, when a vector is of constant length, you take the dot product and it will be some sort of constant squared. So let's go back to here. Why is it that this thing here, constant length, when you take dot product, it equals some sort of constant. Whereas here, when you try and take dot product of this, it won't be some sort of constant. So we need to address this. But wait there, before I do that, bear with me. I need to adjust this. Wait there. Okay, so why is it? Bear with me. Why is it that when something is of constant length, it will be some sort of constant when you take the dot product? Whereas this one here, the magnitude changes, but we can't say when you take the dot product of this thing, we can't say it equals some sort of constant. So let's try and look at this scenario here. So let's say the vector is here. So the vector, so the across here, let's say it's of radius a. So we can write the vector here as this thing here, because crosswise, so let's say we're looking at this vector here. So this length here would be a cos t, and then the height will be a sine t. So this is our vector here. When you take the dot product of this exact same vector, it will be this times this, which will be this, and then plus this times this. That's pretty much the definition of the dot product. So that will then give us this. But in this scenario here, we can factorize the a squared. So this thing here equals 1. So here is when you take the dot product of something of equal magnitude, it does indeed equal to some sort of constant, but the same won't be true over here. So over here, let's just imagine this is of length A and B here. So let's say this is our vector here. So going across would be A cos t, and the height here would be B sine t. So this is our R here. Take the dot product. So it will be this times this, and then plus this times this. That will then give us this. But here you can't factor out a constant, because here's a squared, b squared. Over here you've got a squared and a squared, so you can factorize out the a squared. So this whole thing here equals 1. So it does equal some sort of constant. Whereas over here, you can't. The same can't be said for this scenario here. Okay, I will continue in the next video.